Right now, somewhere inside your phone, a single electron is taking every possible path at once. Not one path, every single path you could ever draw. Through your screen, around the back of the moon, looping through last Tuesday and back again. And the most unsettling part? Scientists can prove it. This is the idea that won Richard Feynman a Nobel Prize. It powers your microwave, your GPS, the laser at the supermarket checkout. And yet, by the end of his life, Feynman quietly admitted something extraordinary. Even he didn't really understand why it worked. The maths is flawless. The predictions are perfect. The reality underneath? Properly broken. Welcome back to Curious Physics AU. I'm going to walk you through the strangest theory Feynman ever published. An idea so odd that decades later, Nobel Laureates still argue about what it actually means. By the end of this video, you're going to look at a coffee cup, a footy ball, even your own hand, and realize the universe is hiding something underneath all of it. Let's get into it. Here's how you were taught the world works. You kick a Sharon off the boot, it travels in a smooth arc, and it lands in your mate's hands 20 meters away. One ball, one path. Newton sorted that out 300 years ago, and we've been teaching it ever since. The ball doesn't accidentally fly through the goalposts, then around the moon, then come back. It goes where physics tells it to go. Every car on the M1, every cricket ball at the SCG, every plane crossing the Pacific obeys this rule. One thing, one route, one outcome. It's the most reliable idea in all of science. Or at least, that's what we thought. Because when physicists started peering into the quantum world, the world of electrons, photons, individual atoms, that nice, tidy picture absolutely fell apart. Right, hold on to something, because this gets strange fast. There's a famous experiment, probably the most famous experiment in physics, actually. You fire single electrons, one at a time, at a barrier with two thin slits cut into it. Behind that barrier sits a detector screen. Common sense says each electron picks one slit, slips through it, lands somewhere on the screen. After thousands of electrons, you'd expect two neat stripes, one behind each slit. Boring, predictable, Newtonian. That is absolutely not what happens. What you get instead is an interference pattern. Bright bands and dark bands stacked across the screen. Exactly the kind of pattern you only ever see when two waves are crashing into each other. But here's the kicker. You are firing one electron at a time. There is nothing else there, nothing for it to interfere with. So what on earth is each lonely electron doing on the way from the source to the screen? And this is where Feynman walks in and drops a bomb on physics. Feynman's answer was so unhinged that when he first proposed it, half his colleagues genuinely thought he'd lost the plot. He said, the electron doesn't take one path, it takes every path, every single one. Through slit A, through slit B, through both slits, around the back of the experiment, off to Saturn and back. Every conceivable trajectory you could possibly draw between the source and the screen, the electron explores all of them, all at once. Then, somehow, all those paths add up. They cancel each other out in some places, they reinforce each other in others. And what we measure on the screen is the residue, the leftover. What's left after every possible history of that electron has been considered by the universe? Imagine you text your mate to meet you at a pub in Fitzroy. Normally, he picks one route. Maybe he drives down Brunswick Street, hangs a left, parks out front. One trip, one arrival. But Feynman's electron? It's like your mate simultaneously taking every possible route to that pub. Through the city, around Albert Park, via Bendigo, even straight through the bottom of Port Phillip Bay. All at once. And the version of him that walks through the door is the sum of every single trip he could have taken. It sounds invented. It sounds like science fiction someone scribbled on a napkin. Except, and this is the bit that breaks people, the maths predicts the experimental results perfectly. down to the decimal point. Better than any other theory humans have ever come up with. Feynman called it the sum over histories. The universe, he said, is constantly adding up every possible thing that could ever happen. Now stop for a second. Let that land. Because your phone, your microwave, every laser, every transistor, every chip in every device you've ever owned, they all rely on this being true. Take the sun, for instance. Our sun shines because hydrogen nuclei smash together in its core and fuse into helium. But classically, by old textbook physics, those nuclei should never get close enough to fuse. They're both positively charged, they repel each other ferociously, and the temperatures inside the sun aren't quite high enough to force them through that wall. By all rights, the sun shouldn't work. So why does it? Because some of those hydrogen nuclei take a path through the energy barrier, a path that classical physics flat out says is impossible. It's called quantum tunneling, and it is exactly what you'd expect if particles really do explore every conceivable route, including the ones that shouldn't exist. The sun is quite literally a star powered by Feynman's strangest idea. Without sum over histories, the sky goes dark. Closer to home, the GPS satellites guiding you from Sydney to Wollongong rely on quantum effects to keep their timing right. The tunnel diodes inside semiconductors, the flash memory in your phone, the chemistry of life itself, the enzymes inside every cell of your body use quantum tunneling to function. Photosynthesis in the gum tree outside your window relies on it. The way migrating birds navigate across the Tasman uses it. Right now, while you're watching this video, billions of particles inside you are taking impossible paths through impossible places, and you are alive because of it. Strip Feynman's strangest idea out of physics, and the universe doesn't just look different, it stops working. But here's where it gets genuinely uncomfortable. If a particle takes every possible path, then which path actually happened? The honest answer? None of them did. Until something measures it, the electron has no history. There is no story of where it went. There's only a fog of possibilities, and that fog only collapses into something definite at the moment we look. Think about what that actually means. The past, the real, concrete past, isn't fixed in the quantum world. It only crystallizes when something interacts with it. Reality, at its deepest level, is not a film playing forward in one direction. It's a cloud of maybes that hardens into a single answer only at the point of observation. And this is where Feynman himself starts to look a bit uneasy in his own interviews. Because here's the dirty secret of modern physics. The maths of sum over histories is perfect. We use it every single day. It built the modern world. But ask a physicist, even a Nobel Laureate, what it actually means, and you'll get 6 different answers from 6 different scientists, all of whom are convinced the others are wrong. Feynman himself famously said that nobody really understands quantum mechanics. He didn't say it as a joke, he said it as a confession. He could calculate it, he could win a Nobel Prize for it, but he couldn't tell you, with a straight face, why nature would bother computing every possible path the universe could ever take just to get a single electron from one spot to another. Some physicists think every one of those paths actually happens, that there are parallel universes branching off at every quantum event, and we just live in one slice of an infinite tree. Others think the paths are pure mathematical bookkeeping, useful for predictions, but not real in any physical sense. Some think the act of measurement creates reality from raw possibility. Others think reality was always there, and we're just terrible at perceiving it. There are physicists at major universities right now, today, in 2026, building entire careers arguing for one of these views over the other. 60 years on, and there is still no agreement. None. Not even close. And that, right there, is Feynman's strangest legacy. Not that he gave us a theory, plenty of physicists do that, but that he handed humanity a tool that works perfectly, while quietly admitting that not a single human being on this planet, including the man who invented it, could properly say why it does. So what's the takeaway? Maybe it's this. The universe you see, the chairs, the trees, the stars overhead, isn't really made of solid stuff. Underneath, it's made of possibility, of every alternative version of every moment, layered on top of each other, cancelling and reinforcing until what remains is the thin slice we call reality. Every time you walk across the room, somewhere in the deep maths of nature, every other possible step you didn't take is being calculated. Every conversation you almost had, every door you nearly opened, every train you didn't catch. The universe quietly accounting for all of it, simultaneously, every single second. We are walking through the residue of trillions of unhappened histories, and we don't even notice. Feynman gave us the equations. He just couldn't give us the meaning. And maybe that's the most honest thing any Nobel Prize winner has ever said about the universe. That the closer you look, the stranger it gets. If your brain is fizzing right now, you're in the right place. Hit subscribe, drop a comment with your wildest guess at what's actually going on underneath the maths, and stick around. Cheers. See you in the next one.